All right. So now let's deal with the workarounds. How are we going to avoid carbocation rearrangements? And there's going to be multiple methods, and you'll need to know how to predict products and provide reagents for each of them. And as we go along, I will tell you what mechanisms I will emphasize. Sometimes I will draw a mechanism just for your information. So to convert OH into a good leaving group, we have a reagent called phosphorus tribromide, or PBr3. And what this reagent does is it converts the OH into a good leaving group, but not such a good leaving group that it leaves right away. So you never get a carbocationic intermediate, and you replace the bromide and you get inversion of configuration, which is consistent with an SN2 mechanism. And so what appears to happen here, phosphorus is like nitrogen in that it can be bonded to three things and still be neutral. The oxygen, and I wouldn't expect you to be able to predict this. This is more for your information than something I care to ask a question about on an exam. Oxygen attacks the phosphorus and you break a phosphorus-bromine bond. The driving force for this is the fact that oxygen-phosphorus bonds are actually quite stable. You get an intermediate that looks like this. And all of this is a good leaving group. Now, you may ask, why doesn't that up and leave like water does? And the answer is, I don't know, other than the data tell you that it doesn't. So that's unsatisfying. Your text doesn't resolve it. I am unsatisfied by that. This is a memorized detail. But in the next step, after you've turned OH into a good leaving group, bromo kicks the good leaving group off via an SN2 reaction, and you get the product shown. Okay? So if you need to convert an alcohol into an alkyl bromide, you can do that with PBr3, and you get SN2. So you avoid the carbocationic rearrangement. Okay? Method 3 is related, and you can use it with PBr3. You can use it interchangeably with PBr3. This is thianil chloride, or SOCl2, and it looks like this. A sulfur doubly bonded to oxygen with 2 bonds to chloro. And then for this particular reagent, you actually need a base. The answer as to why you need a base for thianil chloride but not for PBr3 is not given in your text. I don't know what the answer is, other than presumably it was necessary to make the reaction go. And this highlights a point in organic chemistry where sometimes having a reaction work is more important than understanding why it works. Now that's unsatisfying for those of us that like to know why, but if your goal is only to make molecules, maybe you don't care why, only that you can make molecules. So this reaction proceeds in a very similar way. You end up getting the chloride with inversion of configuration, which suggests that the mechanism is SN2 and does not go through a carbocationic rearrangement. I will show you the mechanism here, though I will, just for your information, I don't intend to ask you questions about this on the exam. Oxygen attacks sulfur and chloro leaves. At this stage, because you have a base present, that's the pyridine, it probably removes this proton. Acid-base chemistry is fast when it can occur. Oops, missing a carbon. Do I expect you to know that? No, I do not. I am simply showing you what happens for your information. At this stage, chloro comes in and attacks. Chloro that left in the first step, Cl- comes in and attacks from the backside to give you inversion of configuration. And then what happens next is kind of neat. As the oxygen's leaving, its electrons kick down to form an oxygen-sulfur double bond, and chloro leaves. So it's like the leaving group is a super good leaving group because on its way out, it falls apart into something that can never come back because SO2 is a gas. Now, all of that's kind of cool, but again, if you want to learn the mechanism, go for it, but I'm not going to ask you about it. Perhaps this is a memorized detail. Instead, just take that SOCl2 and pyridine, convert the OH group into the alkyl chloride with inversion of configuration. Okay? Other questions so far? I can see in your eyes you don't believe me that I'm not going to ask you questions about these things. Should I do that, you simply tell me to go back and look at minute whatever it is of this particular lecture when I told you I would not do it, right? Okay, yes?
Sorry, what concept were you explaining these two examples? I'm not really.
Okay, this...
I heard everything you said, just the competing.
The theme is avoiding carbocationic intermediates whilst doing substitution reactions with alcohols. So the point is, whereas before, if we used HBr, we would lose stereochemistry. Here we keep the stereocenter, or rather, we don't get a racemic mixture of enantiomers. Yeah, that's the whole point. Yeah.
So I guess why is there two different, like it seems like PBR, what's the difference between PBR and SOCl in terms of like avoiding the, like?
They both work just fine. Is there a difference? Why would you want to use one reagent versus the other? Nothing that there would be no distinction that we would worry about. Again, it would be a sort of case by case, which works best for a particular molecule. You could use either one. You should be aware and predict the products question. You should be able to predict the product correctly with correct stereochemistry. If I were asking you to provide a reasonable reagent for a particular process, you would just look at what the product was, like, oh, is it a chloride? Okay, then I have to use SOCl2. Yeah. Okay. Other questions? Yeah.
Is it just these two that we should be aware of, or are there others?
Oh, I'm sure there are others, but those are the two that... There's actually one more that I'm going to tell you about, but those are the two that we've talked about so far. Okay? Yeah?
Is the goal more so avoiding carbocations, or is it avoiding the racemic mixture?
Is the goal avoiding carbocations or avoiding the racemic mixture? Yes, both. We want to avoid carbocations because we want to avoid the racemic mixture. The other reason we want to avoid carbocations is the possibility of rearrangement. Yeah. Okay. So as an example, we could do this same situation we saw before, right, where a rearrangement was possible, where you have, if we had a secondary carbocation there, we could do the 1,2 hydride shift. If you use, say, PBr3, you can very easily get just the desired product and not the other ones, because you never go through a carbocation, intermediate. Okay. So method 4,
Yes.
But yeah, method 4. This is also a method that avoids a carbocationic intermediate. Is make the tosylate. That is a new word. So let me demonstrate about making the tosylate. Suppose you have a starting material like this. You can use a reagent called TSCl and a base called pyridine. The pyridine base looks like this. We used it before in the SOCl2 reaction. TSCl stands for, You ready? Paratoluene sulfonic acid. Para refers to the fact that the sulfonic acid part and the methyl group are opposite each other on the benzene ring. Toluene is a benzene ring with a methyl group on it, and sulfonic acid is this sulfur group attached to two carbonyl oxygens, or rather doubly bonded to two oxygens, and then with an OH group. This is an acid. Its conjugate base is paratoluene sulfonate, and the pKa of this acid is really quite I'm showing you the acid, not the chloride. Okay, that's all right. Take a minute. What I've drawn for you here is paratoluene sulfonic acid, and we'll abbreviate that TSOH, and its conjugate base is the tosylate anion. And the pKa of this acid is really low. It's like sulfuric acid or so on. So just think of this as organic soluble sulfuric acid. It's a strong acid that we can use in organic solvent. But by the fact that we're saying that this is a strong acid, we're also saying that this tosylate anion is a good leaving group, because remember, good leaving groups are conjugate bases of strong acids. Yeah?
Why is it a TSCl and where's the chlorine in it?
Where is that coming from? Yeah, I'm going to show you that now. TSCl is paratoluene sulfonyl chloride. So we're going to take the OH from TSOH and we're simply going to replace it with chloride. Okay? TSCl. And what this is going to allow us to do, and again, mechanism here is not something I care about, though I'm showing it to you to describe what happens. Oxygen will attack the sulfur and chloro will leave. That will give you an intermediate that looks like this. And I'm going to draw the structure of the intermediate here, but I'm also going to say at this point that we can abbreviate all of this as T little s. Okay, and so now we're going to have a base. Likely the base is here. The first thing that happens, the fastest thing that happens is we remove that proton, and that will get us to the following product. Now, notice what we've done here. We have converted OH into a good leaving group, but we haven't changed the stereochemistry. In part because we never had backside attack. OH was the nucleophile here, not the leaving group. Contrast that with what we did before with PBr3 and SOCl2. We used this reagent to turn OH into a good leaving group, but then we had a nucleophile that immediately replaced that via backside attack. So we would get inversion of configuration. Same thing with SOCl2. With TSCl, for whatever reason, once we get here, this intermediate is stable. Now, for those of you playing along at home, you may have noticed that Cl minus left, and so your burning question as well as mine is, why doesn't Cl minus just attack from the bottom to give us the chloride? I got nothing. It seems like it should be able to happen. It doesn't. Don't know why. That's a memorized detail. And again, that's an issue of something that's synthetically useful. but we may not know the answer to. Okay, so you're going to use PBr3 and SOCl2 when you want to convert an OH into a good leaving group, the halide, with inversion of configuration. You're going to use TSCl when you want to turn the OH into a good leaving group, the tosylate, without inversion of configuration. And the other nice thing about tosylates is they are shelf stable, meaning you can store them indefinitely. Yes?
So up in the, like, where the pyridine attacks, it looks like it's attacking the hydrogen, so would that be more like elimination than?
Would this be elimination? Well, sort of. This is a proton transfer reaction. It's just acid-base. We're taking an acidic proton on a positively charged oxygen and we're getting rid of it. Just removing it. Yep. Others? Yeah.
Like the big difference is on this one, like the oxygen is never ever kicked off, it just kind of changes.
Yep. Big difference is the oxygen's never kicked off. It just gets bonded to something other than a hydrogen. Yep. So let's think about using these three methods strategically, okay? Suppose I wanted, and I'll use the same example that we just used. Suppose I wanted to get the following molecule as a product, okay? What pathway would work? Well, if I first converted the OH group into the tosylate using TSCl and pyridine, then I could turn the OH into a good leaving group without inverting stereochemistry. And then in a second step, I could use a nucleophile, Cn- to do the SN2 reaction where we would attack from the backside and we would get inversion of configuration. Right? Now, what if I wanted the diastereomer? What if I wanted Cn- to be up? Then I can't use the tosylate method because when Cn- comes in, the tosylate has the same stereochemistry as the alcohol, so Cn- is going to come in from the bottom. So what I have to do instead is I could use PBr3 or perhaps SOCl2 and pyridine to first replace the OH group with the bromide, and here you get inversion of configuration. And then I would do the subsequent SN2 reaction with cyanide and get another inversion event, which puts the Cn up. So two different strategies to get two different stereoisomers. This pathway up here via the tosylate gives us only one inversion event. So our nucleophile is able to be down relative to where the OH group was. This second pathway is double inversion. We have one SN2 reaction followed by another SN2 reaction. Our nucleophile ends up with the same, in the same up position as the OH group was. So if you've got all of those details in your mind, you can begin to do synthesis in a strategic way. This is going to require you to memorize that PBr3 and SOCl2 give you the corresponding alkyl halide with inversion of configuration, but that TSCl gives you the tosylate with retention of configuration. You don't change the stereocenter. Okay? I generally ask a question about that kind of strategy on the exam, so that's worth going back and working on. And I'm just disclosing all of my evil secrets. Okay, so now a word of advice about reactions, because you're going to find from this point on and throughout 352, we're just going to be handing you reaction after reaction. And as I've said before, if you can organize in your mind how and why reactions happen, that's a good way to be able to navigate through. Nevertheless, when you're given a reaction where I tell you, we don't really know why this works, and then you sort of have to fall back on memorization. And what I recommend in that case is that you do whatever works for you for memorizing, but whatever you do, you ought to be familiar, or rather have mastered these reactions in 3 different directions. That is, starting material and reagent, and then you provide the product. And you could imagine making a flashcard like that with the answer on the back. But that's not enough. You should also do starting material and product, and then you fill in the reagent. That's going to help you with synthesis questions where you think, okay, I need to make this particular kind of bond. I need to get this product. What reagent makes that happen? And then an advanced level is product and reagent, but think backwards to what the starting material would have been. Or, well, sorry, that's not any more advanced than these 3. But this is thinking of the reactions in 3 different ways, right? Forwards, reverse, and then sort of in the middle, what was the reagent? And then to really challenge yourself, you could do something like this, where you have a product and then you put 2 question marks there. Because there may be multiple ways to get a single product, and it might be good to have all of those options sort of collated somewhere. So I never made flashcards when I was in the class. For some people, flashcards are just not that useful. Who wants to go buy little note cards anyway, unless you actually like note cards? But the idea is, can you master each reaction in all of these ways? You haven't mastered a reaction until you can think through all of this. Okay, so that should be what you're working towards. Questions? Okay, well, forging onward. We now are going to talk about elimination reactions of alcohols. These reactions are going to be similarly unsatisfying from a why point of view, and I'm sorry. So the first elimination reactions of alcohols. The first option is, again, use an acid to convert OH into water, a good leaving group. Now, the conditions we're going to use here are sulfuric acid, and you're going to ask a question which I'm not going to have an answer to. So here is sulfuric acid. You can use either sulfuric acid or you can use TSOH. They're interchangeable, just depends on whether you want to be, from your point of view, they're interchangeable, just depends on whether you want to be in water or organic solvent. As we saw with the SN1 chemistry, whoa, I don't know what I'm doing there. Your first step is to remove the proton from the acid to give you, to turn water into a good leaving group. The second step is that water leaves to give you a carbocation. And then the third and final step is that the water that left comes back and removes this proton in an E1 style fashion to give you the alkene. All right, couple of things. First of all, when you use sulfuric acid as a reagent, you may not know this, but sulfuric acid comes in a bottle in aqueous solution. You don't really ever have pure sulfuric acid, and so always assume that water is present here. Okay, TSOH you can use in organic solvent. So, but if we're using sulfuric acid in aqueous solvent, then we've got a lot of water around. It's like 55 molar water. Your text, once you get to this carbocationic intermediate, your text will show the bisulfate anion acting as the base to remove this proton. And presumably they do that because it's got a negative charge. But sulfuric acid is a strong acid, which means this conjugate base is pretty weak. And judging by the fact that you've got a whole lot of water, perhaps way more water than sulfuric acid, in my mind, it's reasonable for water to remove the proton. In the end, it's a difference without a significant distinction. I really don't care what you use as a base to remove this proton. But your product would be the alkene, H3O plus, and HSO4 minus, which is really the same thing as saying water and sulfuric acid. You may be wondering at this stage, why does water not attack the carbocation and go right back on? Indeed, that does happen, and that's just the backward step. This is an equilibrium reaction. And you will see in chapter 10 how actually all of these steps in water with sulfuric acid are equilibrium reactions, meaning we can start with the alkene and we can go backwards to the alcohol, or we can start with the alcohol and go forwards to the alkene. Right now, we're just going to worry about the forward direction, and this reaction is called alcohol dehydration. You're removing water from the alcohol to get an alkene product. But in chapter 10, we're going to turn around and do the reverse reaction. That's going to be troubling to you because I just told you we could go forward. Now we're going reverse. Whenever that happens, what we mean is we're controlling the reaction conditions, usually via Le Chatelier's principle, to get a desired outcome. So in this case, the alkene often has a often has a much lower boiling point than the alcohol does, which means you can actually distill off the desired product, and that will push the reaction to completion. Go ahead.
What happened to like the positively charged, like basically the water molecule? That's like, why does it get replaced with an H? Like, why do the electrons just like?
Sorry, where does water go? Water leaves.
Why?
Because it's a good leaving group. Do you remember in option 1 from the previous hour, once we protonated the alcohol, it left and then Cl- came in? We're doing a similar thing here, only the counter ion is not Cl-, it's the HSO4-. Yep. And then we're just here doing an elimination of a beta proton. Okay. Now, because this reaction proceeds through a carbocationic intermediate, this is susceptible to carbocation rearrangement. And we're not going to talk about that again here because we did the last hour. If we hadn't, we would have pretended for the first hour like carbocations were just fine. Then I would have pulled the rug out from under you at this stage and said, actually, this has been going on the whole time. And then you would have had to go back in your mind and try to unlearn things that you had already learned. So I'm hopeful it's going to be a little bit better having seen the horrific complexity from the beginning. All right. Yes?
When you say it's susceptible to carbon-cation rearrangement, you're talking about the figure in the top right, correct?
Figure, the carbocation?
Yeah.
Yes.
Okay, wouldn't that just be the same molecule?
Yes, it would. What I'm telling you is that this class of reactions is susceptible.
Okay.
Yeah. What I mean by that is, okay, let's suppose you want to take our example of carbocation rearrangement that we've chosen, and we want to use sulfuric acid to do an elimination reaction. We're going to get first this carbocation, then we're going to get, it's going to be in equilibrium with the corresponding tertiary carbocation via a 1,2 hydride shift. And then we can get elimination products from all of these. So here is a beta proton. Nope, sorry, that's not a beta proton. Here's a beta proton, and in red is another beta proton. So from this non-rearranged carbocation, we could expect to get this product or alternatively this one. And then the other ones we could get would be from this one, which would give you this intermediate. And then if we removed this beta proton, I'm just going to highlight that in blue. That would actually lead us to this same product. Whoa. So if you're using sulfuric acid conditions where you go through a carbocation, you're going to be in a situation where you could do a rearrangement. Go ahead.
Going back to the previous example when you first showed us the elimination of alcohol, you said sulfuric acid or the tosylate thing. Is that without a purity with it?
So this isn't TSCL. This would be using the acid form of tosylate. So TSOH, you would protonate the OH group, water would leave, and then at this stage, probably the counter ion TSO minus, or perhaps water could do the elimination step.
So the TSCL with the purity is specific to substitution, and TSOH is specific to elimination.
So TSCL and pyridine we use for substitution. TSOH we use for elimination. Yes. Yeah, sorry. I looked at the clock and I was like, oh, have I kept you here past noon? Yeah. You would say something, right? You would totally say something.
I wouldn't say anything.
You just continue to.
I wouldn't be here.
That's right, good.
It's happy flashes.
Yes. This has nothing to do with anything. I've got a neighbor who is dealing with prostate cancer, and he asked me and another neighbor to come over and give him a blessing. And he was trying, before he was sort of explaining what was going on, but he was talking really sort of slowly and deliberately, and his wife, who normally says nothing, is just sitting in the room. And he starts out, you know, he meant to communicate that most men that live to an advanced age have some form of prostate cancer, though it doesn't tend to kill them. And so he's saying that most men that live to my age, and then he's pausing, and his wife says, are dead. Which was so funny coming out of this woman who hardly ever says anything. So, as I told you, it had nothing to do with anything.
That's going to be on the exam, right?
Yes. Uh-huh.
One more question. Is pyridine specific the base that we need for these, or could it be a whole cascade of
Is pyridine the specific base? There's probably a whole lot of other choices. The thing that's going for you here is pyridine is not a good nucleophile because if it were attached to a carbon, it would be permanently positively charged. So it's a good choice for a base that you don't want to do other things. Okay, so if we want to avoid carbocation rearrangement in our elimination reactions, we do have a workaround, and that's the no carbocation workaround. I'm going to introduce a new reagent, but we will not worry about the mechanism other than to say that it is E2 because there's no carbocation. So I'm going to give us, let's see, this secondary alcohol adjacent to a quaternary carbon. If you use the reagent POCl3, and again, we need a base. We're going to use pyridine as the base. That will give you just the desired elimination product. And it will not give you any rearranged products. If you want to see the mechanism on that, you can consult your text, which shows you it. Again, you're going to be troubled by the idea, why doesn't a potential substitution reaction happen? Because basically this reaction turns OH into a good leaving group, but that leaving group doesn't leave, and then you do the elimination reaction. Why doesn't substitution compete? I don't know. I got nothing, but presumably the reaction works. So what we're testing here in this area is not so much the why, but your ability to use reagents that you know how they work and you know what they do to come up with a sensible synthetic strategy. So if my desired product was this alkene, a bad pathway would be to try to do this reaction using H2SO4. Because again, if I did that, I would have a carbocationic intermediate, which would be in equilibrium with a more stable tertiary carbocation. And then I would get E1 products from both of those, instead of just the one desired product without any rearrangement. So, alternatives, right? With each of these reactions, predict the products, provide the reagent, guess the starting material, and given only products, see if you can think backwards. All right, anything you want to ask about that? No? Good. Yes?
Sorry, in the last reaction you just drew the equilibrium.
Yeah.
This is an example of carbocation rearrangement, right?
Yes, this is a 1,2 methyl shift.
Where is the hydrogen on the other side that would move over?
The hydrogen doesn't move over. It was there implied but not shown. It's the methyl group that's moving
Oh,
over.
it's the methyl group.
Yep. Yes, gross. All right. So the last subject in this chapter is the one exception to having negatively charged oxygens be leaving groups. And we won't have a huge amount of time to get into chemistry, but I want to show you the structure of this molecule. This is a special class of ethers, and it's called an epoxide. So here is the epoxide. It is a 3-membered ring containing oxygen. It's an ether. It's a cyclic ether. We'll usually draw it like this. This molecule is called ethylene oxide and is actually used industrially in polymerization reactions. Epoxides are, as you might expect, electrophilic at these 2 other carbons that are adjacent to the oxygen, in part because they're electron poor because of oxygen's electronegativity, and the LUMO would be the carbon-oxygen sigma star. Now, you can already detect a potential source of complexity in the sense that the epoxide is reactive at 2 carbons. In this case, we've just chosen one of them. I'm sorry, in this case, the 2 carbons are identical by symmetry, so it's not an issue. But just as a preview, we will learn how to deal with what happens when the epoxide is not symmetric and which of those 2 carbons is the reactive one. Now, epoxides will undergo substitution chemistry with nucleophiles, and a nucleophile can attack the sigma star, and the leaving group can leave. Now, that should trouble you today because I told you that a negatively charged oxygen, especially on a localized negative charge on an oxygen, is not a good leaving group. Nevertheless, this can happen in SN2 fashion with inversion of configuration. And the question is, why? And the answer is relief of ring strain. When that 3-membered ring pops open, the energy of the system goes down because you no longer have the extensive ring strain that's present in the 3-membered ring. And that pays for the fact that O- is not the best leaving group. Okay, this is the epoxide. This is the opened up epoxide. And then afterwards, there's usually an aqueous workup step Workup means after you do, you maybe don't understand this now, you'll get it in 353. After a reaction's done, in many cases you add water to extract all the undesired side products, and then you isolate your desired product. The point of adding water at this stage, and sometimes your text will show you water as a second step, but all they're doing is protonating the negatively charged oxygen, and that will give you, that will give you the molecule in which you have a nucleophile and an OH group on adjacent carbons. Sort of 1-2 substitution pattern of nucleophile and OH group. All right. Now, you've heard the term epoxide or epoxy before, most likely in the context of glue, like Gorilla Glue, or perhaps in the context of like making a surfing board, right? Surfboard, surfing board, yeah, clearly I don't know what I'm talking about. But I think that people that make those sometimes use epoxy resin to do what? To actually build the board or make it shiny? I don't know. Yes, tell me what.
Coat the outside so it doesn't get water.
Okay, to coat the outside to protect water from being on the inside. Thank you. I did live in California for 3 years during my postdoc. I did see a lot of surfers. I did not surf myself. I probably do not have the coordination for that. So sorry about that. But yes, epoxides are used in glues. So I'm going to take just a second and show you how. This, again, is not to memorize, but I do want you to be able to see how glues work, because all of you will probably use some kind of glue based on epoxy in your lifetime. So here is the epoxide component of your epoxy resin. Here is the 3-membered ring. This is a linker between the two. For those of you who care, this linker between the two is called bisphenol A, or BPA, and you may have heard about that in the news as an undesirable component of things that, like plastics for baby bottles. We can talk about that later. So epoxy resin comes in 2 things, right? If you go buy JB Weld or something else, you often have 2 different syringes, one filled with the epoxide, the other filled with the curing agent. And the curing agent is a nucleophile. It's a diamine. So you've got the epoxide that has 2 epoxy groups on it, and then you have a nucleophile that has 2 nucleophilic groups on it. And what we're going to do is we're going to use one of those nucleophiles to open up one of the epoxides, and then we can use that nitrogen again to open up another epoxide. And then we can do that again on the other nitrogen. So by the time we're done, we now have a single nucleophile linked to 4 different epoxides, each of which is also linked to another epoxide. So can you see where we're going here? We're building up a huge network of what used to be epoxides and amines, and I've drawn it all orderly to look like that. But it's actually a lot messier than that, as chains are attached to different things. But that rigid structure is then what forms the clear coat to surfboards and what forms the glue in like JB Weld or other kinds of epoxy glues. All right, memorize that and be able to reproduce it on the test, right? No, do not.